Alright guys, so today we're going to start talking about projectile motion, and projectile motion basically is just a free fall problem where you actually have two-dimensional motion. So not only are you moving in the y direction, but you're also moving in the x direction. So a few important things about projectile motion, then we'll start looking at specific problems. And the first important thing we need to understand about projectile motion is that we ignore air resistance when we're doing these problems. So just like we talked about with free fall, the math is going to be more accurate when we're dealing with fairly heavy objects that are fairly aerodynamic and moving at relatively low speeds. Second important thing we need to realize is that velocity is constant in the x direction. So remember we said this is a free fall problem, and for a free fall problem the only force acting on an object is going to be gravity. And gravity is a vertical force, so that gravity is going to affect the velocity, change the velocity in the y direction, but it has no effect on the velocity in the x direction. So once you have a velocity in the x direction for a projectile motion problem, that velocity will stay constant until it hits the ground. And then the second thing we need to realize is that acceleration is constant in the y direction. Since the only force acting on our object is going to be gravity, the only acceleration is going to be the acceleration due to gravity. And so the acceleration in the y direction is going to be negative 9.81 meters per second squared, if we're calling down negative, which we usually do, which is approximately negative 9.8 meters per second squared, which is also approximately negative 10 meters per second squared. So when we're setting up these problems, we're going to have constant velocity in the x direction and a constant acceleration of negative 10 meters per second squared in the y. The other important key for any projectile motion problem is that we can deal with x and y components separately. So in other words, we can analyze our horizontal motion and we can analyze our vertical motion. Now for the horizontal motion, the x component of our velocities, displacements, accelerations, remember we said velocity is constant and acceleration is zero. So the only real equation we need is the average velocity equation. So average velocity is our delta x over t, our displacement in the x direction, divided by time. Or a lot of the times the way we'll end up using that equation is rearranged so that it's solved for delta x. So the horizontal distance it's traveled at any given time will be its horizontal velocity times the time it's been in the air. Now for the vertical components, or the y components, we have constant acceleration. And since we have constant acceleration, we can just use the kinematic equations. So Vy equals V naught y plus AT, or delta y equals 1/2 Vy plus V naught y times t, or delta y equals V naught y t plus 1/2 AT squared, or Vy squared equals V naught y squared plus 2a delta y. And so we can deal with our horizontal components using our average velocity equation, or our vertical components using the kinematic equations. So when I'm doing projectile motion, dealing with projectile motion, I think of it as three basic problem types. And the first one I classify as a horizontal launch problem. So when I talk about a horizontal launch problem, what I mean is that we go up on top of some building or cliff or whatever, and we take an object and we throw it off the top of that cliff, but we throw it straight to the side so that its initial velocity is straight sideways. Now, once we throw that straight to the side, it's going to move out to the right, but it's going to start to accelerate downwards. And so it's going to follow a parabolic path that will look something like this. So, it will travel some distance before it hits the ground, and that distance I call delta x at the end, because the end is when it hits the ground. That's also commonly referred to as a range. And it's going to start with some height, and so we end up basically with the height that it starts out is going to be negative delta y at the end, because whatever height it starts, let's say it's 100 meters, at the very end when it hits the ground it will have fallen 100 meters. So that height of the building or cliff that it starts out on will be the negative delta y at the end. So remember, with any projectile motion problem, we're always going to split up our horizontal information and our vertical information. And so with this type of problem where it's horizontal launch, one important thing to realize is that that constant velocity in the x direction is just going to equal the initial velocity of the projectile. Because it was thrown sideways, Vx is equal to V naught. And then also because it was thrown sideways, for our vertical components, we know that V naught y is equal to 0, because it was not thrown up or down at all, it was just thrown out to the side. Okay? A couple other things that are important for us to realize is for any projectile motion, A is going to equal negative 10 meters per second squared in the vertical direction. Okay? And then, like we said up there in our drawing, delta y at the very end is going to equal the negative height of the cliff that we started on top of. So here we have an example problem. We say a ball is thrown horizontally at 25 meters per second from the roof of a 10-meter tall building. How far from the base of the building will it strike the ground? So the first thing I like to do is draw a picture of the problem. And so there we have our picture of the problem. We're starting on top of a 10-meter tall building. We're throwing it out to the right at 25 meters per second. It's going to follow a parabolic path down towards the ground, and we want to know how far from the base of that building is it going to hit the ground. Now once we've done that, the next thing we want to do is look at what do we know in the horizontal direction and what do we know in the vertical direction. Okay? So for the horizontal direction, we know one thing. We know the value of Vx. We know that Vx is 25 meters per second. Then we're going to look at our vertical component. And for our vertical information, we know that delta y at the very end is going to be negative 10 meters. We also know that A is negative 10 meters per second squared, approximately. And we also know that V naught y is equal to 0 because we threw that horizontally. And then of course, what we're looking for at the end is delta x. We want to know how far does that ball go? What is delta x at the very end? Well, the only way to solve for delta x is to take our Vx times our t. And we know the value of Vx. The problem is we don't know the value of t. So what we're going to do is use our vertical information to solve for t and then plug it into the horizontal component. And that's a very common strategy to use for a projectile motion problem. Use either the horizontal to solve for t, plug it into the vertical, or use the vertical to solve for t and plug it into the horizontal. So if I want to use the vertical information to solve for t, then the best equation to use is going to be delta y equals V naught yt plus 1/2 at squared. And fortunately for me, V naught y is 0. Rearrange for t, and that is the square root of 2 delta y divided by a. So in this case, that's going to be the square root of 2 times negative 10 over negative 10. And the square root of 2 is 1.4 seconds. So now I'm ready to solve for delta x. So delta x, like we said up here, is Vx times t. So delta x then is going to be 25 times 1.4. So the value of delta x is 35 meters. Alright, so that's it for projectile motion today. We've talked about projectile motion in general, and we've talked about the first problem type, which is a horizontal launch, and we'll talk later about the other two types of problems.